Hello everybody, today we're going to have a look at surds and see how they fit together with your understanding of number and algebra. So surds are used to solve a variety of problems in number and algebra, quadratics, geometry and trigonometry, and they're used to describe some irrational values precisely. Not all of them, we can't do pi or e or I with the surd, but we can do lots of others. Surds have specific properties used for simplifying and expanding, and they follow many of the algebraic solving and index laws. So let's have a look at some of the things you need to know. You need to know that root a times root b can be placed under the surd symbol and the a and b multiplied. We know that root a times root a equals a, and we know that we can collect like terms with surds. A root c plus b root c will equal to a plus b root c. And we'll do some examples of these in a second. We also know that sometimes we can go backwards from this step, or this step, when we know the square number, we can work backwards. So if we have the root of 9, 9 can be expressed as, the square root of 9 can be expressed as 3 in the same way that 3 squared can be expressed as 9. We have some connections to index laws. So we know that the nth root of a is equal to 1 on n. A to the 1 on n, and it follows from that that the nth root of a to the power of m is equal to the nth root of a all to the power of m is equal to a on 1 on n all raised to the power of n, and a to the power of m raised to the power of 1 on n. Now we can look at all of these in a second, along with the Dobbs rules. So a squared take b is equal to a squared take root b all squared. And once we have a difference of perfect squares, we can expand it as follows. And we can also use a surd to rationalize the denominator of a fraction. So a on root b equals a on root b times root b on root b just being 1. And then we'll end up with root b times root b, which will be b, and so on and so forth. So let's look at these now that we have them, and we'll keep referring back to them to make sure that when you put this into your notes, that all of them make sense and you know where to use them. So we'll start with root 18. Now when we're simplifying a surd, what we're trying to do is to find multiples of square numbers. So in this case, the square number will be 9 and root 9 root 2. And we know that the square root of 9 is simply, what's the square root of 9? 3. 3 squared is 9, times by root 2, which more simply can be written as 3 root 2. Similarly here, we can use root a times root b as root ab, and that'll give us root 60. Then we'll have to think for ourselves for a second, think, all right, well, what square root can we go in there? Well, maybe we can do 4 and 15. So root 4 root 15, which will give us 2 root 15. Root 5 root 3 can't be simplified any further. Let's look at the next one. Root 8 can be root 4 root 2. We know that root 4 is a square number, plus 5 root 2. And we know that 18 is 2 root 9. Root 2 root 9, I should say. So this will simplify to 2 root 2. Root 4 is 2. Plus 5 root 2. Take 3 root 2. And then we can collect like terms. 2 lots of root 2 plus 5 lots of root 2 is 7 lots of root 2. Take 3 lots of root 2 is simply 4 lots of root 2. Looking at the next one, multiplying two brackets. 3 times, well, we can think about this as 3 times root 2 times 5 times root 3. Putting the whole values together, 3 times 5 will be 15. Times by root 2 root 3, which is root 6, which will give us 15 root 6. Root 2 root 3 won't simplify any further. This is a bit of an interesting one. So we would go root 3 plus 2 root 2 multiplied by root 3 plus 2 root 2. Or we could have used perfect squares, but either's fine. So root 3 times root 3 will give us 3. Root 3 times 2 root 2 will give us 2 root 6. 2 root 2 times root 3 will give us 2 root 6. And 2 root 2 times 2 root 2 will give us 4 times 2, which is 8. 2 times 2 is 4. Root 2 times root 2 is 2. Which will simplify to 11 plus 4 root 6. Simple enough. Now here what we're going to do is we're going to use difference of perfect squares. So we can restate this as a squared take root 5 all squared, which will be a take root 5 a plus root 5 by DOPS. And we can do something similar to this one. We can go root 5 a all squared take root 7 all squared, which will give us root 5a take root 7 root 5a plus root 7. In this case, we might be wanting to rationalize the denominator, so we're going to multiply by root 3 on root 3, 5 on 2 root 3 multiplied by root 3 on root 3. In doing so, we will end up with 5 root 3 on the top and 2 times 3 on the bottom, which will be 5 root 3 on 6. Simple enough. This time we're going to have to use a difference of perfect squares. So 1 on 1 plus root 3 multiplied by 1 on 1 take root 3. And what we'll find that this is 1 on 1. The take root 3 plus root 3 will cancel out. And then you'll end up with take 3, which is negative 1 on 2. That worked out quite nicely. Oh no, it didn't. Oh yes, it did. Oh no, it didn't, because what have we missed out? Well, I suppose what we've missed out is that we can't multiply by just any old number. We have to multiply by 1. So you have to remember to do 1 take root 3 over here, which will change this to be 1 take root 3. And we will end up with negative 1 take root 3 on 2. Which I suppose we could simplify further to root 3 take 1 on 2. Just by changing the sign of the numerator. Now in practical examples, we can first look at how to find this line here. So we have an equilateral triangle of side 2 with 60 degrees in each of the angles and a perpendicular bisector which splits the bottom one into 1 and 1. Now if we just look at the right hand side right angled triangle, using Pythagoras we can see that the third side is simply jumping steps. 2 squared take 1 squared. So x squared equals 2 squared take 1 squared, which is 4 take 1, which is 3. So x must equal root 3. And from that, using our trigonometry, we can say that the sine of 60 is equal to root 3 on 2. The cosine of 60 is equal to, let's say, adjacent over hypotenuse, that'll be a half. And the tan of 60 is equal to opposite over adjacent, which will just be root 3. Now we're going to use these values in the next problem. And you'll find that exact values determined in this way, because you can also determine the same for 30 degrees using this triangle, and similar examples can be done for 45. So it's an easy way of remembering these exact values so that you'll be asked to do later. Now let's see this in practice. So we have a right angled triangle here, and we want to find out x. So opposite over hypotenuse is going to be sine. So sine 60 is equal to opposite, which is 9 on x. We can rearrange this to be x equals 9 on... Actually, it's not easier to do it that way in this case. Let's just substitute sine 60 first. We know from here, sine 60 is root 3 on 2 equals 9 on x. So we can rearrange this to be x equals 9 times 2 on root 3, multiply both sides by x, divide both sides by root 3, multiply both sides by 2. So x will be 18 on root 3, which we can rationalize. So that will be 18 root 3 on 3, which will simply be 6 root 3. 18 divided by 3 is 6. So there you go. There's a bit of a walkthrough of predominantly what you should already know and how surds can be used in different ways. I hope that's helpful, and I'll stick it up for everyone. Thank you.